Welcome to lecture number 62 of the course on nonlinear structural analysis, theory and applications. So, this is the second and final invited lecture by Professor Rickles. In this lecture, he is going to talk about nonlinear structural analysis, multiphysics structural simulation with supplemental damper systems. So, basically applications of some of the concepts that you have learned in this course in multiphysics structural simulation with supplemental damper systems. With that, over to you, Professor Rickles, and thank you again for accepting my invitation.
Hello everyone, my name is James Rickles. I'm a faculty member from Lehigh University, which is located in Bethlehem, Pennsylvania, in the United States. I'll be presenting to you as my second lecture on nonlinear structural analysis the topic of multiphysics structural simulation with supplemental damper systems. Now, the presentation that I'll follow will first begin with multiphysics real-time hybrid simulation. I'm going to discuss an overview and present some challenges. We'll then look at the multiphysics real-time hybrid simulation of systems. The first one with soil foundation structure interaction, and the second with fluid structure interaction. And then I'll summarize and conclude at the end of my talk. Now, before I begin with the multiphysics aspect, let's just briefly review the real-time hybrid simulation concept. This will be the same structural system I presented in my first lecture, in which we subject that system to multi-natural hazards. And that particular system is shown here as a 40-story building with the outriggers and supplemental dampers, which is shown underneath the facade. Now we have these nonlinear structural dampers again, in which we need to model them. So we're going to have to do this experimentally and model the rest of the system again analytically. So we have the analytical substructure and the experimental substructure. The two need to be coordinated and synchronized through the simulation coordinator, which is going to integrate the equations of motion at each point in time I+1. In doing so, it issues command displacements through the simulation coordinator to the analytical and the experimental substructures. And what we're asking those two substructures to do is very abruptly determine the restoring forces and send those back to the simulation coordinator. And this process, as I had mentioned in my prior lecture, has to be synchronized and done in real time. Upon doing so for that time step, we'll repeat that process for each sequential time step, such that at the end of the duration of the event, we have the real-time structural simulation. So what is shown here is this for one time step I+1. If we want to look at wind loading, in this case this is aerodynamic wind loading, predefined, we can do so by redefining the right-hand side of the equal sign that is on the equations of motion, the forcing function. Time steps. We need to have this whole process remain synchronized, and so everything has to be done within the time step, completed within the time step for each time step. If that's not done, we're going to get inaccuracies and potential instabilities. And the time steps are proportional again to this digital controller speed, and typically we have time steps of the order of 2/1024 to maybe as large as 6/1024, depending on the accuracy and the size of the system. Multiphysics computations. They're very challenging. Shown here is a soil foundation structure interaction, and I'll talk next about fluid structure interaction. In terms of the former, the modeling of the soil foundation system as a numerical substructure using the conventional finite element method, particularly in real time, is computationally prohibitive. You can see here the number of degrees of freedom for this particular foundation, over 1 million because of the number of elements and the number of nodes associated with that system. If you look at fluid structure interaction, typically it's done with computational fluid dynamics, CFD. To do that in real time is computationally prohibitive, if not impossible. Here again is a typical fluid domain in which the structure is shown. The fluid domain has got many elements, and it results in this particular case over 1 million degrees of freedom. So to do that in real time is going to be very, very challenging. Now, shake table testing may be an alternative. However, the payload capacity is typically limited, in that it's difficult to include the large structural system and the foundations to enable synergistic investigation. In terms of wind tunnel testing, we typically have to test at reduced scale aeroelastic models, and having embedded response modification devices in these models, very difficult. They can interfere with the aeroelasticity, or we may have incompatible scaling laws with respect to these reduced scale response modification devices. So let's move on then to the multi-physics real-time hybrid simulation, showing how we overcome these challenges. First, soil structure interaction. Do we need to consider it? Well, it can be beneficial or may be detrimental to the performance of structures during earthquakes and severe windstorms. Knowledge generally is lacking about soil foundation structure interaction and how it affects the response of a structure, and in particular the efficacy of response modification devices during a natural hazard, such as an earthquake or a severe windstorm. And I'll actually illustrate this for an earthquake here in a bit. So let's first focus on the soil structure interaction, looking at the structure that I had presented last lecture, in which we came up with a very well-behaved structure with response modification devices, in which we reduced the design-based shear and still got resilient behavior. This is the same structure before, with moon-resisting frames and damped brace frames, in which there's non-viscous dampers placed in the damped brace frames, the DBF. So let's consider now the multi-physics simulation. Shown on the left would be a finite element model of the complete system. What we're going to be doing here is have to face the challenges. I already mentioned these challenges. Prohibitively, if not impossible, to compute this in real time. And we can't really use a shake table because of the payload problem. So our solution is neural networks. We're going to model the soil foundation structure interaction by accounting for the system of the soil and the foundation through neural network modeling. The rest of the system, we'll see what we're going to do. And in fact, it's shown here. We're going to go ahead and model the soil foundation domain using the neural network substructure. So this is a new substructure added to this process. So in the simulation coordinator, we have the restoring forces, the internal restoring forces, RI capital NN. This is now a new term. That neural network is going to be having as an input the interface displacements and velocities. That is the interface between the foundation and the structural system, in addition to the external excitation forces, in this case from the earthquake. We're going to have the same experimental substructure as before, in which we're going to have dampers modeled, but since we have 3 dampers in the system and only 1 physically modeled, we're going to use online model updating, which I don't have really time to talk. It's beyond the scope of this presentation, but here we're looking at using an unscented Kalman filter with information from the experimental substructure to update an explicit Maxwell model of the damper, and the references for this are shown in the lower left-hand side, particularly the second one, which is a published paper. The analytical substructure is very similar as before. We're going to have finite element models in which we have force-based fiber elements, panel zones, and lean-on columns for geometric stiffness. Talk briefly about the neural network architecture. Shown on the right is the architecture for an LSTM, long short-term memory. This is a neural network that's going to be used to model the soil foundation domain. It works very well for temporal data. It consists of a number of gates, so forget the input and the output gates. We have the cell states, and we also have some hidden states. W and B, what are those? Those are the weights and the bias. Those have to be obtained through training of the neural network. So we're going to have to train the neural network, and we're going to do so using the Python environment. These neural network models then will be ported to Simulink and executed in real time. Now, the multi-physics simulation of this soil foundation structure interaction system, shown as the analytical substructure, which is above the foundation, and below the neural network models the remaining part, the soil and the foundation. The analytical substructure will have discrete members and connections. We're going to model the beams with force-based fiber elements, which is going to have RBS connections. So throughout the length of that portion of the beam, we're going to have integration stations that have reduced flange widths. Again, this is documented in the publication on the lower left, engineering structures. Columns will also have force-based elements. We'll have panel zones being modeled, nonlinear elements. We'll have the damped brace frame with moment end releases. That is, we're going to have beams in those brace frames that have end releases, and the diagonal bracing as well. Force-based column elements. And then we're going to have rigid floor diaphragms that connect the mid-bay of the moment frames with the damped brace frames to the lean-on columns. That's a gravity load system. This is basically abbreviated here, gravity load affects P delta. Now, the neural networks. 4 layers of long short-term memory, 1 fully connected layer. We've got 150 neurons per layer. We're going to use regularization and data augmentation with an Adams optimizer. In total, we're going to have 1,094 ground motion data sets, in which 930 used for the training, 150 for validation, and then we're going to use the remaining 14 for the real-time hybrid simulation. Now, in order to train the model, we have to develop OpenSea's models with a complete system. It's a little bit controversial, but I'll tell you how we take care of the controversial aspect. The OpenSea's model is going to generate data that we train the neural network. What's that data? The output at the interface forces, F1 through F6. The input will be the displacement velocities at the interface to the foundation, and the accelerations, the inertial forces from the accelerations acting on the foundation. So the buildings assume to rest on sandy soil deposit having increasing stiffness, where the soil depth is associated with site class D, and the shear wave velocity is 270 meters a second with a soil friction angle of 33 degrees. So we're going to have plinths and retaining walls as part of the foundation system shown in the schematic. The soil domain to the bedrock, it's 125.62 meters in length and 125.62 meters in width, and a depth of 100 meters. So this is 3D but shown in planar. Now the upper 25.5 meters of depth of the soil is modeled because it's influenced primarily by the soil foundation structure interaction. We use a deconvolution technique to convolute the bedrock acceleration up to that depth. Again, the details are in the paper noted on the bottom of this slide. Now, we got to be careful about trapping energy in this basin, this model. So the left and right side, the lateral boundary condition has a stiff soil column, 2 soil columns at each end to mitigate the effects of reflecting wave propagation. We don't want to get energy trapped in that domain because waves will attenuate outwards in the real world, in the real soil. And we're modeling that as such. Type of material for the soil is a pressure-dependent multi-yield material used to model nonlinear areas in the soil domain. You'll find this material class in open seas. We have the ND elastic plastic material for simulating response to the pressure-sensitive soil materials. For generating the training data using open seas, we have to account for the effects of the excavation, the dead weight of the structure and the foundation itself, and the overburden pressure. So we're going to have to do this when we go through and develop the open seas model and then use it to obtain the training data. So to obtain that training data, we first start with building the soil model. We then initiate a wrapper. This is a process in open seas to preserve a state in which we perform lithostatic analysis to get the overburden pressure initiated, in which we then update the Poisson ratio followed by a load controlled analysis. So the wrapper then is such that we have an initial state analysis in which the wrapper is turned off, and we do that load control analysis, where we're going to excavate, introduce the retaining walls, and build the foundation and the structure of alpha self weight. And then we induce the self weight through gravity load analysis. So now we have the overburden pressure, the weight of the structure, and the foundation has been built. It's like we've excavated the soil in the real world. We then add the Rayleigh damping to the system and perform the dynamic analysis. And in doing so, this generates the training data for the neural network that will be used subsequently to train the neural network in Python. Now, let's talk about a real-time integrated architecture, actually the control IT architecture. Shown here is that architecture. We have various workstations. This includes the data turbine. We have a simulation core I mentioned before. We have an XPC. This can be very important. It's a real-time operating system. There's 2 of them shown here, but we only really need to use 1. We have some digital controllers to move the actuators. In this case, we're just going to need 1. We have an acquisition system. This is all connected by SCRAM. This is shared memory. So the real-time simulation architecture, the neural network model, is going to require developing that neural network model. We first develop that and train it in Python using PyTorch. Now what we're going to need to do is to execute in real time. So to do that using integrated control IT architecture, we are going to have to export the neural network model's architecture, or if you want to say deployed, but we're going to have to export that into Simulink, which is going to be residing on a real-time target XPC. So what is Simulink? Some of you may be familiar with this, some of you may be not, but Simulink is a graphical probing environmental tool developed by MathWorks. I encourage you to check it out. It's a pretty neat tool. What it does and why we use it, it's going to generate optimized C++ code that is basically then compiled and run in real time on a speedcode XPC. So this allows us to maintain that real-time execution. And then shown here is the neural network model that's been imported into Simulink. So this has, again, these blocks, and they're connected. We have 4 LSTM blocks. We've got the input and the output of the LSTM model. The output is the forces at the interface, because as the input is going to be the state, the displacements, velocities, and the ground acceleration shown here, and again the outputs on the far right. What we're porting in here is the weights. We have to store these in memory, as well as the bias And that becomes part of the input for each LSTM layer, as well as the daisy chaining the output from one layer to the next. Let me talk briefly about regularization, something that's very, very important. So regularization is applied during the training to reduce the reliance on specific neurons, that is, within the layer. Those little dots that you saw, those are called a neuron. It's kind of like how the brain actually thinks here. What we're going to do is have to prevent overfitting. We don't want to train this thing so well that it's overfitting. And in doing so, we're going to improve the neural network's ability to generalize a new set of data it has never seen, which is really what happens in the real-time rapid simulation. So we implemented regularization to mitigate overfitting. And this, again, assures generalization when a trained neural network model is such that it becomes generalized for a large number of epochs. You'll see what I mean by that in a moment. Now, we use different regularization techniques. I'm not going to go into them, but they were implemented and their effects on the performance of the neural network model were studied. And it's in that paper that was referenced. I'm not going to go through that. I'm just going to illustrate the results in the general sense. So we have dropout, Gaussian dropout, additive Gaussian noise, and kernel regularization. These are just some techniques that you'll find in the literature. So when you do a training of a neural network, for each pass through the network is called an epoch. And shown here is what's the RMSE is the loss of the average of the various passes through. So for each pass, the loss factor is going to be reduced. We hope it is. That means the network is converging. Hopefully it converges to within or lower than the error that you want to achieve. Now what we have here is a bunch of lines on the left side. We have some that are designated LSTMs. That's a long short-term memory of regularization. We have, I think, around 4 of these. Below that, we have the case without the regularization. That's without the regularization. This is with the regularization. This is a training loss. The regularization without it has a better RMS error than with the regularization. Why would we want to regularize? Well, we'll see in a moment. Validation is when you subject the model to now a set of data it hasn't been trained on. And again, it has the same tendencies where the regularization loss curves have a higher error than the ones without the regularization. So again, why would we want to regularize if this is the case? So let's talk about this then. Here is this arrangement. The neural network is shown here. It's part of a closed loop system. We've closed the loop by taking the input to the network, which again is the displacement velocities and the inertial forces. These two displacement velocities at the interface, inertial forces are those acting over the mass of the foundation, and the restoring forces are fed back. They're into the simulation coordinator. So this is a closed loop. And this closed loop is part of a system that starts to interact with the structure. That's the analytical substructure, the experimental substructure, and the online model updating. So we have a situation here. The training is done with open loop. Open loop means we put in the displacement velocities and the inertial force and acceleration, and out comes the restoring forces. And that's fine. We look at the error between what we know happens from the OpenSeas model with what the neural network predicted for that epoch. And we'll go through and repeat that process and hope to minimize matters here. I mentioned it is, however, a closed loop system in rapid simulation. And the interaction effects through the coupling of the analytical substructure and the integration algorithm can produce some ill effects here. So the regularization, as you see, is really required. It's going to ensure we're going to mitigate the overfitting effects and reduce the noise in the simulation. Noise in the simulation is detrimental. Furthermore, we're going to have to achieve accurate results. And I mentioned the word it could be controversial when we're using OpenSeas. What does that imply? What do I mean by that? Well, when we did that OpenSeas modeling, we modeled everything, the dampers and the structural system and the soil. Soil is modeled fairly accurately in OpenSeas, but it can't be done in real time. So we're going to replace that soil in the neural network hybrid simulation to be able to do that in real time. But the dampers are being used, which aren't modeled very well. That's why we're doing a hybrid test to model them physically. So how can an OpenSeas model generate realistic training data? That's where we augment the model assumptions of the damper. We do a wide range of parameters in order to try to bound the potential variation in the properties of those dampers. And that allows us to achieve, hopefully, more accurate results in the hybrid simulation when the properties of the damper, which are not well understood, appear in the problem. So let's now look at some results here. Shown in the upper part of the figure is a real-time hybrid simulation. I call it the hydraulics off. This is where we model everything numerically, including the dampers, but we're going to compare that with a reference solution which has the exact same model except for one thing. That is, the dampers are modeled the same in both OpenSeas, which is a reference solution, and the neural network hydraulics off. The superstructure is modeled the same, but the soil and the neural network models hybrid simulation configuration, hydraulics off, is modeled with the network, the neural network, and the reference solution has that soil model with continuum elements. So you can see when you compare the two, if the neural network is precise, you should get the same answer, and we're not. Displacements, the upper part here of this figure, maybe doesn't look too bad. This is a close-up. But notice something here. As the epochs, that is, you increase the number of iterations, the RMS error gets worse. This is kind of disturbing. You would think that would get better. And for instant accelerations, which typically you are because of non-structural components or even some structural components, there's a lot of noise here. This is almost worthless. So when we regularize or use regularization, guess what? It cleans it up significantly. You can see here the RMS error. Just look at the accelerations here. These are different dropout or regularization approaches here. The error is significantly smaller than what we have as 14% at 325 epochs. Furthermore, the displacement's more accurate as well. So the regularization error is illustrated to be very important. And this shows some of the error that I mentioned earlier with respect to not regularization or regularization being used, and the number of epochs, the error just increases. So that data augmentation, I described, but here it's shown visually. The complete systems model in OpenSeas numerically. We're going to generate data for training, but in the real world, that is a hybrid simulation, these dampers are modeled experimentally. So we're going to have to augment the properties of these dampers in the OpenSeas model to try to capture the range of variation of the properties of the dampers in order to get appropriate neural network training data that sees the variation in the dampers, potential variation that will actually take place in the experiments. It's actually shown here. This is data augmentation, in which the modeling of numerically nonlinear viscous dampers is typically used. It's shown there, the model in the far middle of the right of the slide here. This schematic illustrates the components. So we have coefficients, C sub D, kind of like the nonlinear dashpot coefficient, alpha, which is an exponent, and K sub D, which is related to the elastic compliance of the damper. Well, we did test. And we also did simulations, and you can show here the variation in time of the dashpot coefficient. We see the variation, the stiffness, not the dashpot coefficient. Here we have the variation in the dashpot coefficient. And here the exponent. This is an evolution of the neural network model due to online model updating, which online model updating comes from measured physical data. So for each point in time along this history, the model's been updated, the coefficients have been updated, and you can see that the coefficients are changing. So we have to be careful then to augment our data sets when we generate the training data to account for this potential variation during actual hybrid simulation. So here are some of the damper properties that we prescribed in the nonlinear Maxwell element in OpenSeas. It's a wide range. I think there's 10 cases here, and those are the data sets, and they were used for the various ground motions. Well, let's now see what happens when we account for soil structure, foundation, interaction. What I'm going to show you here are two simulation results. The first one actually is already plotted, and that is it's a fixed base, a real-time hybrid simulation with no soil structure interaction, everything modeled above the foundation as we had done in the prior lecture. What is particularly shown here is for the fixed base, we have the damper force, damper deformation. This is the gray hysteresis. It really shows some characteristics of a nonlinear viscous damper. This is at the third story. We have the moment curvature relationship at an integration point at the end of the left-hand side second story beam. And we can see a few degrees of nonlinearity occurring in the moment curvature. It's got a local ductility of about 2, not too bad, but it's there. This is in the RBS connection where we actually expect, if any, some yielding. Now the roof accelerations. This is a time mystery. This is a fixed base. We expect them to go to 0 at the end of the accelegram. The ground acceleration, which is going to be plotted here when I play this video, is not shown yet. In between those two plots is the roof displacement. And when we look at the roof displacement for the fixed base, looks like it goes back to the initial position. So that implies that the structure has no residual or minimal residual drift. So this design procedure, which I did not elaborate on in my prior lecture, but I did provide references, appeared to be quite successful, and shown here again. And this presentation, by the way, is summarized also in this reference. Now here is the damper. This damper is at the upper floor, and the other dampers are modeled numerically. What I'm going to do here is to do a replay for the soil foundation structure interaction cases. This will be where the curve is going to evolve with a blue color in these plots. And the replay is going to recover at the interface neural network forces and displacements, which I'll then feed into my final element model in the post-hybrid simulation just to observe locally the deformations and the strains and stresses in the soil. So this allows me to recover. It's actually interpretable. So with that, let's go ahead and play this. So what's your impression? What do you think? The soil foundation structure interaction didn't have a detrimental effect here? I think it's quite apparent. If you look at the damper force, damper deformation, the blue curve here has greater force developed in the damper. So the velocities are higher than the fixed base case. and the damper deformations are longer. So if you told the owner, based on a fixed base case, to go ahead and buy a damper that's only got what was for the fixed base case of about maybe 20 millimeter maximum deformation, maybe 30 millimeters, go ahead and buy those dampers. They'll work fine. Design the members around that damper. I think the maximum force here was about 300 kilonewtons. You're going to fail the structural system. The dampers are going to actually pull out because during the soil foundation interaction simulation, the damper deformations are larger. So the load path's disrupted. If that doesn't happen, the damper forces are larger than perhaps what you designed for, and the adjacent members may have a problem in the load path. Look at the ductility demand locally. It's about a factor of 8, so we have considerably more damage, and you can tell this after the earthquake, the building's leaning. The owner's going to be furious with you if you were responsible for this. This shows the panel zone here. I didn't elaborate on it too much, but it shows the panel zone is deformed. The roof accelerations, well, they kind of go back to 0 as you expect, but look at the residual drift. I don't have the number here. It's actually documented in the paper shown at the bottom here, but there is residual drift. And here is that ground acceleration. This is by the way, at the design basis earthquake level. So now let's look at the results here. These are statistics. We actually ran 14 design basis earthquake level ground motions, 7 near field, 7 far field. And what I have plotted here on the left-hand side here is a peak inter-story drift for each story level. We have at the ground level, this is actually the first story, second story, and the third story. The solid thick line is the mean, and the dashed lines are plus or minus 1 standard deviation. So what I'm highlighting here would be 1 standard deviation above the mean, which is the 84th percentile. This is with the fixed base, so we see the mean here. Now, with the foundation soil model, look at what happens. The maximum story drift, the 84th percentile, has it as large as 1.5% compared to about half of that value. Residual drift is an indication of damage and also usually leads to the building being condemned if it's too much. So fixed base, very small amount of residual drift. This building is very close to being almost immediately occupiable because the residual drift is less than 1/500. But look at what happens with the foundation soil included. The mean value here keeps increasing at the roof level. It's about 0.08%. You say, well, a little bit small, but look at the 84th percentile, which is typically what we pay attention to, much larger. So the soil foundation structure interaction cause damage to the structure that's probably going to have to be accounted for and maybe corrected or condemned. And then we have the damper, peak damper displacement here. As I was mentioning, this is the mean value of shown here for the 14 simulations, and the mean plus 1 standard deviation, see it's up around 35 millimeters. And if you didn't have the damper stroke long enough, the damper would pull out because here the mean value exceeds the 84th percentile. The 84th percentile for the soil foundation structure interaction is approaching 55 to 60 millimeters. So what was not accounted for in the simulation, if the dampers were to actually pull out, the load path would be disrupted, the structure would fail. We can actually do those simulations, but we assume the damper had enough stroke for that soil foundation structure interaction. So this is a concern here. So again, significant findings in the residual story drift, the maximum story drift. We also have that accentuated by the foundation rocking, in addition to building deformation, and the damper deformation itself. So the dampers, their efficacy is reduced. Now let's move on to fluid structure interaction. I'm going to look at a tall building with outriggers. I refer to that in describing the overview and the review, should I say, of the real-time habitat simulation concept. So we're going to take that structure, but it's going to be a little bit simplified, in which we have the outriggers and we have the core of the building as shown here. That is core of the building shown here, modeled with force-based fiber elements. And we have the outriggers here with dampers. And we have the fluid flowing here. So this would be wind loading. Here are the dampers. That's the experimental substructure. Analytical substructure looks like it's disconnected, but through continuity and equilibrium compatibility, the dampers, when they go into the equations of motion, they're actually connected. The restoring forces are in equilibrium and transfer the forces through the load path from the outrigger truss, which is shown here, down to the foundation. Now the neural network structure, what's that doing here? The substructure. This is actually modeling the fluid loading. We're going to take the information from the fluid, that's the inlet velocity. We got to also look at the position of the structure as it moves with the wind blowing. And so we're going to look at the displacement position. We found we don't really need to account for the velocity because just having the displacement in real time more or less counts for that. The output from the neural network is the fluid loading, which goes right here on the right-hand side. Analytical substructure is similar to before, input and output. Command displacements go in. What comes out is the internal restoring forces, R sub I. Experimental substructure, something similar. We impose on these dampers these command displacements, and in real time we want the restoring forces. Now, how do we do this? This integration. Well, I don't have the opportunity to go through the details here, but if you look at this reference here, it describes an explicit MKR alpha method. This was also described in the last lecture I gave. It's explicit, which allows us to put the fluid loading in because we know what the loading is at the end of the displacement the time step. We also know the displacement, so we can impose those over the period of the time step, and at near the end of the time step we recover those fluid loadings in that displaced position and then integrate the equations. So that's described in more detail in this reference here. So here's the details of the system here. We actually used a reduced scale because this study actually was part of a pilot study, but don't be disturbed by that. It also works at large scale. But you see, here's a prototype structure. Here are the dampers. They're a little bit different than the dampers I showed in the low-rise building, but they are nonlinear viscous dampers. You can see also the rate dependency, the hysteresis here with the nonlinearities of load versus velocity. Alpha in this particular structure was about 0.8, whereas in the last low-rise structure we had more hysteretic and more of a S-shaped force velocity. That factor was 0.8 for alpha. So the neural network architecture here, a little bit different than what was used in the sorrow structure interaction. We used the gated recurrent unit. It works as well as the LSTM, and maybe we could have used that, but we wanted to use something different. And the architecture shown on the right, it has some gates, an update gate, a reset gate. It has a hidden state as well as a hidden candidate state. And it has the various attributes here that are schematically shown here. So I can let you look into the details further by referring to the paper that I've been citing. As before, we're going to train the neural network in Python, which is a really nice tool for such a task. But then we're going to export, or should I say port that to Simulink, where it could be executed in real time. Python is not deterministic in terms of executing in real time, and we need to have synchronized real-time deterministic calculations. So the Simulink environment has to be used. So you've seen this schematic before. This is an actual one used to generate the training data. shown above are some of the details of that. We actually use the arbitrary Lagrange-Orlean formulation, and we used a program developed by Professor Kaliintis from University of Houston. Working with him, he's our colleague. We did the computational fluid dynamics with him and obtained the training data. And the fluid discretization, we did do a mesh conversion study and arrived at these fluid elements called bilinear quadrilateral elements, about 26,000 of those, of just over 26,000 nodes. The density of the fluid and the kinematic viscosity was shown there. The reason we chose those particular properties was for illustration purposes, where we want to ensure that the Reynolds number corresponding to the maximum inlet velocity, we're talking about fluids here, so Reynolds number is important here, remains below 2,000. So to remain in the flow regime that's laminar. And we actually had the unsteady laminar regime, so we did get vortex shedding, and you'll see this in a moment. But most importantly, we want the structure to develop some sufficient lateral drifts. We also adjusted the modulus of the structure, so we have some meaningful fluid structure interaction, as opposed to having very rigid structure and the fluid flow by. That is not very challenging. You probably don't need to use computational fluid dynamics in the sense we are. It could be all predefined. So look at different training and validation data sets, look at different frequencies of the incoming fluid. Again, in the modeling there, we first used open seas with the fluid dynamics calculations coupled to that, where the nonlinear Maxwell models were used to develop the training data. The inlet velocities are shown there in the Young's modulus, so the members are varied. And we had 81 unique parameter sets created with the training and validation, 70 for training, 11 for validation, and the remaining ones, which I don't give a number here, but there were 6 we used for hybrid simulation. Now, one thing I want to emphasize, the wind loading is going to be, I think, around 20 to 30 seconds real time. Each simulation, that is, we ran this, not OpenSea, I have to correct myself, but this ALE code on the TAC supercomputers. Tim Cockrell is the director there. He allowed us to have access. We really thank him for that as part of the NEARI network. 100 hours to do one simulation. Now, fortunately, we could do them in parallel. So we did all 81 in parallel, but 100 hours. That shows you the relative scale in time. No way you can do a computational fluid dynamics in real time. You have to do it in 20 seconds in real time, or 30 seconds, whatever that may be, and it takes 100 hours. So this is where the neural network is very beneficial. It tremendously speeds up the calculations. Now, there's a few things we have to consider. Here's the fluid domain. These are just idealized mesh. We have the solid structure here, which is going to be modeled with force-based fiber elements. So we're not going to model necessarily every discrete member in the layout of a truss. It's really a cantilever type member, column here, type structure. So we have the fluid. There's actually the outside part of the structure. That's the interface. We have interface nodes there, which basically define the fluid pressures that we have to then transfer those to the force-based fiber element that's acting at the core, where the structural nodes. So in the end, given the fluid pressures that we get from the computational fluid dynamics during the hybrid simulation, we actually transform those to forces acting on the structure, and those are those fluid forces I alluded to earlier. And this is described in the paper shown here at the bottom of this slide. Here are some results. This is showing the drift, time history, in the lateral direction, of course, the roof drift, and this is a vertical displacement. Now, why can it be a vertical displacement? How can it be? Because there's traction, there's actually friction along the interface, so there is some vertical movement, but it's very small compared to the lateral drift. This is percent, this is actually millimeters. So the building is undergoing up to about 2.5% story drift. Now we did a Fourier transform of this, and this is actually after 5 seconds in. So this duration, I have to correct myself what I said before, it's about 50 seconds long. Still much shorter than 100 hours, which took for the computational fluid dynamics experiment simulation. Back to the Fourier transform. This is frequency plotted against the amplitude of the Fourier transform, and we see a dominant amount of energy here. This is the period of the inlet velocity of the fluid, and then we see these other quantities here. Let me go to the next slide and explain this here. These other quantities, these are high frequency oscillations at integer multiples of the inlet velocity of the frequency. This occurs in fluid structure interaction. This interaction is induced by the structure of the vortical fluid occurring. There's actually vortex shedding here. So this is in the lateral direction. This is in the vertical. The vertical tends to decay at the higher frequencies. But the lateral, again, this is a dominant frequency for the fluid loading. This rises before it dies. Why is that? Well, the answer is right here. There's a fundamental natural frequency of the structure at 2.2 hertz, right around here. And this is where we're getting dynamic amplification of the motions of the structure. So this is the dynamics and fluid structure interaction. This shows for each damper, there's one on the left and one on the right side of the building in the outrigger system. We have the force versus the deformation. You know, we start at the, somewhat near the origin because there's initially some deformation due to the gravity. But then we have, after 5 seconds, we have the accumulation and the deformations evolving over the time history, and it's kind of anti-symmetric because of the left outrigger and the right outrigger. There's a line of symmetry, but it's actually a line of anti-symmetry about the midpoint of the structure because the building deforms like this. This dampers in compression, this dampers in tension. The dampers are not exact, they're actual dampers, so we see some similarities but some differences. This is why they're actually modeled physically. And you see the energy dissipation occurs or it helps reduce the drift. I'm not going to go through those details, but it does help control the drift like it does in this shorter buildings. Now, this is actually a data-driven neural network model where the output is data, the input's data. We have done physics-informed neural networks, PIN, but this is not. So in PIN models, it's claimed that they're interpretable. You can kind of explain why what happens. Here we have outputs. What happened? What's going on with the fluid? We only know the structural response. But we can answer that question if we take the replay form. This is something we developed where we take the neural network as an input to the interface that was the final element model of the fluid. So we have the structure, and at the interface of that structure is the fluid pressures and the motions. We take those as input to the mesh of the fluid and replay that. And so we're going to impose those histories, and guess what we have? This is at what point in time here. Here shows the vortice magnitudes. We see there's the structure is moved at this point in time. I think it's around 25 seconds. We have some vortex shedding here, and you can see the vortices coming off. Perhaps here at the corner is where there may be some, high pressures cladding here, but you can tell exactly what's going on in the fluid and the structure. So this is this replay feature, which just allows us to better interpret what goes on in the structure and how the fluid is behaving around that structure. And so with that, I'd like to summarize this multi-physics real-time hybrid simulation and conclude also what I presented as advancements in real-time hybrid simulation. This is combined with nonlinear analysis, of course, and they were presented where neural networks was used, thereby extending the integration algorithms, the explicit formulated force-based fiber elements. I explained those in my last lecture. I didn't go through the real-time adaptive hydraulic actuator control, but that's needed and it's documented in the paper. All those are put together through these multi-physics simulations to solve multi-physics problems. And if you haven't figured it out by now, what is multi-physics? It's the different elements of nature. We have soil, water, air. You talk about temperature. We have solids, which is the structure. Those are elements of nature. Those are the multi-physics. So a well-trained neural network model has potential to model this multi-physics phenomena for conducting these simulations in real time. And we feel that the methodologies that are presented here, this is rather new material. It's just been published here in April 2026. Although it's not quite April, it will be in one or two more weeks, but it is available online currently. This enables these large-scale hybrid simulations to be conducted where the structure has high complexities. And this is going to allow us in the multi-physics regime to lead to new discoveries and knowledge for coming up with solutions to mitigate the effects of natural hazards and develop innovative concepts that promote resiliency. I'd like to now offer my acknowledgments. The research that was presented was one that was performed at the NEARI Lehigh Large-Scale Multidirectional Hybrid Simulation Experimental Facility. This facility is sponsored by our federal government through the auspice of the National Science Foundation through 2 cooperative agreements whose numbers are noted on the second bullet. In addition, the NSF, that is the National Science Foundation, sponsored research that was performed at this facility under the 2 award numbers noted on the third bullet. I'd like to also acknowledge Fazil Malik. He is a Lehigh University PhD graduate research assistant who performed the research as part of his research dissertation, and I feel did an excellent job. Furthermore, the Texas Advanced Computer Center, who offered their facilities and resources, allow us to do the computational fluid dynamics simulation. The director of that facility is Tim Cockrell. Finally, the nonlinear viscous dampers that were used in the low-rise 3-story structure in conjunction with the soil structure interaction simulations were provided by Taylor Devices. And I want to thank you for your attention, and I hope I enlighten you more in terms of the applications of hybrid simulation and looking into the future where you can use artificial intelligence to model things that are nonlinear even faster than the conventional means, but you have to be very careful. I think nonlinear analysis, the way we do it now with discretely modeling things, you're going to be very comfortable and can count on the answer because you could model things discretely. But if you have to do things in real time, it requires a lot of effort, and you can't do that in real time, such as soil and fluid. And neural networks is an option, but you still need to get really accurate training data through nonlinear analysis. So if you have any questions, feel free to contact me. My email address is noted near the bottom of this slide, and my personal email address as well. So with that, I want to thank you for your attention, and I hope you again gain further insight into nonlinear analysis.